Hi everybody, this is Dr. Bricker here with a video introduction for our next lab, diffraction grading P&W. So go to Pivot Interactives and log in, and then we're going to be doing the diffraction grading P&W lab. So I clicked on that, and it looks something like this. So this video below shows the apparatus we will use to explore the diffraction of light. So remember what diffraction is. The wave-like characteristics of light comes out when the light goes through a small opening. So you get things like interference and diffraction. In this lab, we're going to be doing a diffraction grading. So basically, it's a substance that has a whole bunch of little slits in it. So when you shine light on this diffraction grading, the light has to squeeze through the small openings, and the wave-like behavior of the light comes out. Us personally, we never experience that. We never go through really small openings. We go through a doorway. Our own wave-like characteristics don't come out. But light, on the other hand, can fit through small openings, and wave-like behavior does come out. So it says here, watch the video to see how the apparatus is used. Take note of the diffraction pattern created on the screen when the diffraction grating is placed in front of the laser. So let's take a look at that. I'm going to make this bigger. And then you can hit play, just like you've seen before with these videos. We can take a look at it. Okay, so there's laser light going straight to the screen. Nothing's happening. The diffraction grating has not been put in yet, and they're about to put it in. Okay, and now the diffraction grating is in. You can see a bunch of different bright spots. Let me actually advance it a little bit. So see, here's the central maximum. Here's a bright spot, bright spot, bright spot on the going to the right, going the other way, same thing, same distance away. So diffraction grating is making the wave-like behavior come out because the light has to squeeze through these small openings. And then they're spraying some stuff there so you could actually see the laser beams. Okay. So I won't play the whole thing for you, but basically in the lab, we're going to be able to measure these different angles and see how things work out. We're going to have different lasers we can use, different wavelengths for the lasers. Okay, you can open up diffraction of laser light. First examine the properties of diffraction gratings and see how changing the grating spacing and wavelength affect the amount of diffraction. So remember from class, this is the equation that governs the behavior of diffraction grating. So m times lambda, lambda is the wavelength, is equal to d times this theta, sine of theta, and then this little index here, m, goes along with that. Okay, so left-hand side of the equation is measured in units of length. So the right-hand side has to be measured in units of length. So wavelength is typically in nanometers. So this d here has to also be, in units of length. So if the left-hand side is nanometers, the right-hand side is nanometers. Because m is just a number, sine of theta, same thing, it's just a number. Okay, so in this equation, m is the order of the image observed. We'll see a picture of that in just a minute. Lambda here, it's the wavelength, and d is the separation between the slits. And then theta sub m is the angle that goes along with the different orders. So it looks like this. Here's the screen back here. Here's the laser. Here's the grating. So this is the central maximum, m is equal to 0. And then you get another bright spot here when m is plus 1. You also get one over here when m is minus 1. So this distance is the same as this distance. Actually, they're all spaced out the same. And you got plus 2, plus 3, plus 4. So when m is equal to 1, you have theta 1. That's that angle. When m is equal to 2, you have theta 2. So it's just an index describing which one we're talking about. So little m here is not the mass. Usually we're used to that like in physics 220, for example, but here m is just the one that you're talking about, the order. Okay? And the one shown in the picture is m plus or minus 3. Okay? So equation 1 did have that variable d, and it's the spacing between the lines. So d is the length between the lines. Okay, so if you take the length of the grating divided by the number of lines or slits or whatever you want to call it, you get what d is. Sometimes people that work with these things a lot have a grating value, and the grating value is just 1 over d. So d is the inverse of the grating value. Okay, so the grating value would be something like 100 lines per millimeter. So to get d, you'd have to take the inverse of that. Okay, since you're using visible wavelengths, typically measured in nanometers, you might have to turn this into nanometers. Okay, so here's a grating, what it might look like. I mean, not literally, they're a lot smaller than that. The figure shows a diffraction grating with the value of 5 lines per millimeter. Okay, so that's not, 5 is not d. You'd have to do 1 millimeter divided by 5 to get what the value of d was, right? Because d is a unit of length. Actually, I think I gave that one away. That's okay. You have to, I think, figure out what that is here. Calculate the value of d, okay, in the space here. Do it in millimeters and then also do it in nanometers. So you can try to type it out if you want to, or do the work on a piece of paper, take a picture, and then you could upload the picture here. Okay, or you can type it out if you want to. It's just a little cumbersome with Pivot Interactive to do that. Okay, and then after that, now we'll examine the relationship between grating spacing, wavelength, and diffraction image angle. So the video below shows lasers with 3 different wavelengths. So we've got wavelength 405 nanometers, that's violet, 532 green, and then red is 635. So going from left to right, these are less energy, right? Bigger wavelength means less energy. And then grating values of 100, 300, 600, and 1,000, that's lines per millimeter. So to get D, you've got to take the inverse of all these because you need millimeters per line to get the value of D in the equation. Okay, so we've got another video here, and you can change things around. You could change the diffraction grating value. So again, that's not D. You've got to take the inverse of this to get D. Or you could change the wavelength around. So you've got all these different values here. And same idea. You could hit play and see what happens. Maybe I'll make it bigger. Just so you see what it looks like again. So that's where the diffraction grating is. Now we actually have some tools here. You can take this, this and move it around so you can measure these different angles. So you want to put this lined up right where the laser is, and then right, if you can, right barely in front of the diffraction grating. So something close to this. There's some ways to fine tune this. You'll see it in just a minute. But you can see this angle here. So this is the green laser. You get like 32 degrees for that one. Looks like we're only able to see one of them here. Okay, yeah, good. So that's we're only seeing like the m is equal to 1 part here. Okay, go back to the lab. So first, you're going to examine how changing the slit separation affects the diffraction angle. So we want to first start with the red laser. So that's 635 and 100 lines per millimeter. 635, 100, load. Same thing, you might have to fine tune where this measuring device is. Okay, so they're putting in the one. Oh, now you can really see it, huh? And if you want, you can pause this, and you'd be able to measure these angles. Maybe you got to adjust this a little bit. You want this line here to be right where the laser was coming out, and then you want that to be just in front of it. And then you can see the angles are a lot smaller. The wavelength is a lot bigger. We've got the formula. You see why that works out, or you will when you examine it in more detail. Okay, so you've selected the red laser, 100 lines per millimeter, play the video. Rewind, advance the video until the laser has just been turned on, but before the grating is placed. The only tool you have is the protractor, so you can put the protractor wherever you want to, carefully aligning the 0 mark. So before you actually put the grating in there, make sure that you have it lined up. Here's the fine tuning. So if you want to move it a little bit to the left, hit the A on your keyboard, D to the right, W for up, S for down. Okay? Good. So a little bit more fine tuning than just grabbing it and moving it around there. Okay, continue to advance the video until the diffraction grating has been put into place, but just before the light turns on, just before the room lights turn off, move the projector up and down so the horizontal base is directly aligned with the side of the grating facing the screen. Okay, so line everything up just as it says here. And then continue to advance the video until you can clearly see the diffraction rays that create the m is equal to 1 image. Measure to the angle to the nearest 0.5, and then you can put this in data table 1, which you'll see in just a minute. Okay, so is it 1, 1.5, 2, something like that. So a little bit of estimating. It's kind of hard to see. Just do the best that you can with that. And if you really wanted to follow proper experimental technique, you might measure the angle between the +1 and -1 image, and then divide it, or ray, and then divide it by 2. But in some of the videos it's hard to see the -1 part. So we're just going to use one of them. Okay, so data table 1 is down here. Okay. Okay, now we want to switch to the next grading value, 300 lines per millimeter. So if you wanted to get D, it would be 1 divided by 300, and you'd have the answer in millimeters. Repeat your measurement for the m is equal to 1. Leave the protractor on the video and reposition as needed. Okay, and then you could measure the angle for this, and measure the angle for this, and measure the angle for that one. Okay, this is all with the red laser, and then you just increased the number of grading lines per millimeter. In doing so, did you increase, decrease the value of D? So you'll have to think about that. If you increase the grating spacing, will that cause more diffraction in the laser light or less? So more means it spreads out more. Briefly explain using your data as evidence. So don't just say you think it is. Like, you can refer to, well, when I had 100 lines per millimeter, this happened, compared to some other lines per millimeter, this happened. So use your actual data to support your conclusion here. Okay. All right, excellent. And now it says here, now select the video trial with 405 nanometers, so violet laser, and then 100 lines per millimeter grading. Again, measure the angles for m is equal to 1 and record it in this table. So this is table 2 here. Keep the same grading and complete the table. So keep the same keep the same grading, but use these 3 different laser lights. Measure m is equal to 1. Okay, so we're keeping the grading value the same, but we're changing the wavelength, and then you have to come to some conclusion about what happens to how the light spreads out. So does increasing the wavelength cause more or less diffraction? Briefly explain your answer using your data. Okay, you've got the equation. So you see how it should work out. You'll actually do it and see how it does work out. Okay, and then the second part is figuring out the determining the spacing of an unknown grating. So how are we going to do that? Same video that you had before. We're going to measure the angle for images when m is equal to 1 and m is equal to 2 for each of the lasers and complete this table below. So the table is already set up for you. So violet wavelength 405. What's the angle for the first order? What's the angle for the second order? And then what's m times the wavelength? So this would just be this one here. 1, that's what m is, times the wavelength, times 405. So that would just be 405, and it's in nanometers. This space here would be 2 times the wavelength. So 2 times 405, that would be 810 in nanometers. Same idea here, m times the wavelength. Once you get the angle that you measure, then you take the sine of that angle, and that goes in this column. So why are we doing this? Why do we need m times the wavelength? Why do we need sine theta? Let's take a look at that. Okay, so here's the equation we have. M times the wavelength is d times the sine of theta. And what we don't know is the value of d here. Now, if you wanted to, you have m times the wavelength, you have the sine of theta, you have several different measurements. You could go through for every single one of them, solve for d, and then put them all together and get the average. We've used this technique, though. So we're going to make a graph of this. So let me just write this one more time. M times the wavelength is d sine theta. Remember the point-intercept formula we had before? Y is equal to mx plus b. And the m here is the slope. So I already don't like the notation I'm using. So y is equal to the slope times x plus b. I don't want to write another m because you got m up here for the order that we were talking about before. So I'm just doing slope, point-intercept form. Okay, so usually you look at it like this, y, and this is x. And then you'd have a line here. Whatever comes in front of x in this formula is the slope. We've done this a million times already, it seems like. That's what this equation looks like. So if we have m times the wavelength on the y-axis, really the vertical axis, and you put the sine of theta over here on the horizontal axis, and you plotted this, the slope of this is whatever comes in front of the x variable. The x variable in this example is the sine of theta. M times the wavelength acts like y. So whatever comes in front of the sine of theta is the slope, which in this case is actually d. Okay, so you'll get all the data, and you'll have to set up the axis, put the equation of the line there, and then the slope of this line is d. Okay, the value of d. Okay, let's go back to the actual line. Okay, so here's the data table. Here's the wavelength, violet, green, red. Here's the order. Here's the angle that goes along with those. This is m times the wavelength. We talked about that already. And then this is the sine of theta. Now you want to graph that data. Luckily, Pivot does that pretty well for you. So on the vertical axis, well, what do you want to put on the vertical axis? You can put whatever you want on it. So you saw from what I did before when I wrote it down, you really want m times the wavelength to be on the vertical axis. You don't have to worry about the uncertainty there. And then on the horizontal axis, I'm just clicking on it. What do I want to be on the horizontal axis? Well, on the horizontal axis, I wanted the sine of theta. So I could put that on the horizontal axis. And then once you do that, you'll have a nice line. You could name it like m times the wavelength versus sine theta, and then click this little gear button here to include the equation of the line, and then the slope of that is the value of d. Okay, so you don't need to add another graph here. And then the last question or so is just finishing things up. You wish to generate a linear graph from this equation that will allow you to easily calculate this value of d. What quantities will you have on the y and x? Okay, we just went over that. So it's a really powerful technique here. Create the appropriate graph, show the origin, record the best fit equation below. Okay, so it's going to be in point-intercept form, so you could write the equation here. And a little hint here, the magnitude of the slope is rather large today. The slope will be presented using lowercase e as a computer notation of power of 10. So the slope of 1.234 times 10 to the fifth, for example, would be 1.234 e to the plus 5. The e just means times 10. Okay, so just write that down here. And then determine the value of d from this. So the value of d is the slope. And then, make sure you include units for that. And then calculate the grading value. So if you get the value of d, the grading value is 1 over that. And then make sure you put that in lines per millimeter. Okay? Be careful with that because when you graph this, these things are in, m times the wavelength here. This is in nanometers, right? Okay. Excellent. Good. So have some fun with it. You're exploring some modern physics. You're exploring wave-like nature of light coming out. It turns out if you were to take electrons, which actually have mass, and shoot them through small openings, which is possible to do, their wavelength is on the order of the slit opening. And electrons, even though they have mass, do the same thing. They spread out. You might think that they would go right through and hit the wall, but there's a distribution of them. So that's what's coming up in the next few chapters after we do this diffraction interference chapter. Okay, any questions, just send me an email and I'll talk to you soon. Bye-bye.